Hey, Simkins Physics Corner bonus round here with Mr. Simkins. I got a 15-minute limit on my videos because of the free software that I'm using, but I did want to show you guys some graphical examples of simple harmonic motion. In your Albert set that you have to do for this week, there are a lot of questions that involve graphs, but if you keep our discussions from last week in mind and you look at these graphs with the right eye or through the right lens, you can address these sorts of problems. So let's look at a couple samples here, like this one. The speed of an object at time t equals 0.65 seconds. So that's like somewhere around here, because here's 0.6 and here's 0.7. So if you can read a graph, is most nearly equal to which of the following? Well, one of the key things about graph interpretation is always considering what kind of graph are we looking at. This is a displacement versus time graph, or an x versus t graph. And if the question is asking you about speed, speed is distance over time, or in this case, displacement over time is going to be our velocity, but it's just asking us the speed, which is the scalar version of velocity. I digress. The slope, the rise over run, look at what the rise over run actually is. The rise is x over run is t. Rise over run, x over t. Oh, that's going to be our velocity, or in this case, how much distance did we cover in time. And so that is why when it says what's the speed off of this displacement graph, you're going to say, well, it's got to be related to the slope somehow. So it's not the value, that would be dumb. That would be just where you are, not how fast you're going. The slope of the line connecting the origin and the point on the graph at 0.65. The origin, is that talking about over here? That's silly. Yes, that's the speed. No, I don't think so. Can I even erase that, or that's going to distract me? All right, let me get rid of that one because that was a dumb possibility there. Oh, well, I got rid of all my annotations anyway. Oops. Let's go back to the one we're actually looking at and get rid of that line. There we go. Perfect. How about choice C? It can't be choice B because it's just silly. Nobody takes the slope from the beginning of the graph all the way over to the edge there. So it's not choice B. How about C and D? The slope of the line connecting the points where the graph crosses the axis near 0.57, so like here, and near the point of the graph on 0.65, which is like here. And that's a pretty good estimate, right? But check this last one out. D, the slope of the tangent to a best fit sinusoidal curve at 0.65. Now, you might be like, well, there's too many big words for that to actually be the answer. But if you know about oscillating functions, you know that an oscillating function follows that sine curve. And if you're not sure what a sine curve is, technically it doesn't start from here, but a sine curve does do this sort of deal where it oscillates back and forth. You can go ahead and try it out on your graphing calculator. If you hit y equals and type in sine x, you'll see a little sine curve go across there. And then what does this mean? The slope of the tangent to a best fit sinusoidal curve? Well, tangent is that straight line along the edge, right? So while C is a pretty good answer, D is the best answer because it's going to give you the most precise slope at that instant in question, and the slope at the instant in question is going to tell you about your speeds. That's why number 6 has to be D. Let's take a look at the next one. Another example of same graph, but asking a different question with that graph. The total distance traveled by the object between 0.35, so that's like right here, and 0.4 is most nearly. All right, well, this is, can you read a graph? Okay, because this is a graph of displacement versus time. So at 0.35, we're somewhere around here. You notice the labels of the graph are 0 and 4, so that's probably like -2 or something. And then at 0.4, we're probably down here at like 3. So we certainly didn't go 0, so we can knock that one out. We certainly didn't go all the way from 0 to 4, so we can get rid of that one. And so for this short little interval, the best guess is going to be 2. Now you're like, well, you wrote a 2 and we didn't get to 4. Okay, maybe it's 1.5 to 3.5. We're estimating, we're picking the best one, or most nearly. It's going to be most nearly B for that one. And one more quick example of what a graph question might look like. This is important. Whether they give you a velocity, an acceleration, or a displacement graph, because of the nature of simple harmonic oscillators, there's always going to be that repetitive nature of the function. And so if you ever have a graph with time on the axis, that means you can automatically figure out what the period is, and which also means you can figure out what the frequency is, because remember that the frequency is equal to 1 over the period. So for this one, it says the frequency is most nearly. How am I supposed to get that? Well, just look for where the graph repeats. All right, so let's pick a nice clean spot. Oh, look how clean this spot is. Look, you see that hump at the top there? In order for this function to go all the way down and come all the way back up, all right, or in this case, the oscillator to start from 4, go all the way down to -4, and come back to its initial position, that's completed one cycle. Look how clean these data points are. That's from 0.7 or sorry, from 0.2 to 0.7 seconds. So that means that the period is 0.5 seconds. Now, if you were a noob at this, you'd be like, sweet, the answer is A, move on. Not so fast, because the period is 5 seconds, and because of the inverse nature or the relationship between a period and frequency, the frequency is 1 over the period, so the frequency would actually be 1 over 0.5 or 2 hertz. All right, so anytime it's asking you about a graph, look for that repeating pattern. I'd like to point something out to you guys. All of the equations on our equation sheet, let me move my face out of the way here so I can fit both of these equations. Both equations for oscillators, both for the period of a pendulum and the period of the spring, sure, they both start with 2 pi. That's just because of their cyclical nature. And they both have this square root thing, all right? But if a question says, like, what information do you need additional in with this graph? Remember that this left side of the graph you can always get, or sorry, the left side of the equation you can always get by looking for that repeating pattern on the graph. And if it gives you like frequency, then you can find the period. So always remember that frequency and period, you can find those things back and forth from one to the other. Let's remember too that the period for the spring is dependent on the mass and the K, and the period for the pendulum is the L over G. So I've seen some questions, and there's one on your Albert like this. Let me give it to you. They'll give you a graph, right? So from the graph you can get the period. They'll say a mass of 0.2 kilograms is graphed as shown. What is the spring constant K? Now you might be like, how am I supposed to get spring constant from a displacement versus time graph? Well, now do you see how you would do that? Let me change colors to indicate a little bit of a strategy that you could use here. All right, so if a question said, hey, something of mass this, and they give you the mass, 0.2 maybe, and here's its graph, well, the first thing you would do is you would look on the graph and find the period. How long does it take for one cycle to be completed? Now do you see? You have the period, you have the mass, and if it said, what's the spring constant K for this object? You would just use this equation. They could do the same thing for a pendulum. They could say, what is the gravitational acceleration on a planet whose oscillator has a graph that looks like this and has a length of 0.3 meters? You might be like, how am I supposed to get gravitational acceleration from a graph of velocity versus time? Well, this is how you would do it. You would look at the graph, you would look for that, how long did it take for that pattern to repeat? That would help you get the period. And then you would, they give you that third piece of information, if you will, the length, and then the piece of information they ask you for the gravitational field strength, you could solve using that equation. So if you get stuck on any of your Alberts, hopefully you've watched this video. Hopefully this video helped you out a little bit with how to use the graphs to find that additional information plugged into our period equations for the pendulum or the spring oscillator, and that will help you guys be successful in that. Till next time, I'm Mr. Simkins. Make sure you like and sub the channel, hit the notification bell, ring it up so you get the new videos. Until next time, this is the Simkins Physics Corner.